Good afternoon, everyone. Welcome to this third scientific lecture. So I'm Hadrien Bériot. I was recruited here about now 13 years ago by a fascinating researcher, this man over here, Christoph Schramm. Left this wonderful company right after cowardly. Right after he hired me, and I think about 10 years later, after I'd taken responsibility for the research team here, I hired Sophie.
Meaning that too.
That's not what I'm saying. I'm just saying there's a sort of legacy in the three lectures you had this morning, and we tried with Sophie and Christoph to make them coherent and complementary. So I'll mostly about propagation, where Christoph explained the principles, analogies, and beyond. I looked more at the source term. I will look more at the left-hand side of the analogy, the propagation operators. It started. So as I provide an overview of the acoustics propagation model, physical models, ways to solve the operational scheme. There are different classes of input. You can solve on the structured grids, or you can solve on unstructured grids, and you can solve an operator, an acoustic propagation operator in time domain, or you can solve it in frequency domain. And I'll talk about next generation and other aspects, and then I'll in more details how it's spread. I prefer solution methods, namely discussion costs and sources of numerical error. And we will have another session jointly with Simone on Wednesday, if I'm not mistaken, which is more hands-on, where you will have the chance to.
Sorry,
yeah.
You say here that there is an issue with the microphone.
Ah. It's much better now. So should I change anything, or is it fine to continue like that?
You're right.
I think we should also keep
Because I did choose the. That's the one you had, Q to N.
Yeah.
Is it okay, or?
I'm asking if only one has a problem, or if everybody has the same problem.
Or if we have a statistical distribution of people. In which case
the outlier when you.
Oh.
I should probably continue.
Okay, now it seems
Speaking.
better.
Okay.
Yeah.
All right.
All right. Let's move on then. That's a bit of a recap. Was discussed in previous lectures. The different sets of equations can be used for the propagation depending on the nature of the flow and the level of approximation. Again, there are two main approaches, what Sophie called, I think, DNC, and hybrid approaches, and direct approaches. DNCs can be prohibitively expensive for most engineering applications. I hope this was clear from this morning lectures. This is a slide taken from Sophie, just to insist again on the fact that I will mostly focus on this part of the analogy, whereas Sophie described more, the right-hand side in the previous lecture. So I will talk mostly about the propagation aspects. Starting from so this is a bit, I should say maybe a brief word about the lecture and the angle of it. I mean it will mostly be seen from an engineering perspective.
One thing, if anybody is connected online, please mute the microphones.
you connected online?
No.
Your microphone is muted.
Okay. Okay.
And yeah, so we'll you know look at things for more of an engineering perspective. So there will be less equations in this talk and a bit more yeah, practicalities. So some of the assumptions here, you know, may be questionable, but it gives you a bit of you know, first order approximation on how to consider these operators. So if you essentially take D at C, you neglect the nonlinear effects, you end up with the linearized Navier-Stokes equation. You can neglect viscosity and heat transfer, end up with linearized Euler equations that Sophie also mentioned. And then there are a few other operators. There's the APs, which is quite popular these days in the aeroacoustic community, which is essentially a revised version of the LEs, where the hydrodynamic modes are neglected. Then you can also assume irrotational mean flow and obtain a scalar operator, which is also widely used in industry. We refer it to linearized potential equations, LPEs, but it has different names. It's basically describing acoustic perturbations on top of an irrotational mean flow. And if you neglect completely the mean flow, you have the Helmholtz equation. So that's a bit cascading, you know, going down in complexity, the different acoustic propagation operators, convective acoustic propagation operators. About the linearized Euler equations, so they write in conservative form as a very standard hyperbolic equation, and you see it here. The usual unknowns are density, pressure, and velocity, but you can also write it in real conservative form using momentum as variable, and these are basically the AX and BY equations contain the mean flow variable. So U0 is the mean flow in X direction, V0 is the mean flow in Y direction, and you have density, of course, and speed of sound. And you can also solve this operator, I mean, look at this operator in Fourier domain, and then it takes this very simple form. If you put a monopole source in a uniform flow, so we have a simple MATLAB code with all these operators, so we can compare them, and that's quite handy. If you put a monopole source in a uniform flow, so you obtain this kind of result for a uniform flow of Mach 0.6. So you see that the upstream wave is shorter than the downstream wave. Of course, that's a Doppler effect, as you would expect it. That's density. That's X rho ux, rho uy, and that's conservative pressure. So you can consider its pressure, and you see that you obtain.
Sorry, what do you call conservative pressure?
I think it's pressure under Lillis form.
Okay. I don't know.
It's P up to a factor, essentially.
Okay.
It's what we use. It allows you to write then the LEs in conservative form to keep the hyperbolic form. But you just can obtain the pressure from it very easily. And so it's basically pretty classical. Now, interestingly, when you now consider a dipole, so you take as the right hand side, you start from your you basically take the equations that you showed this morning, that Christophe showed this morning, and you solve the LE, and you see that you obtain some in the wake of the source, some different wavelength in this operator. This is something you would not obtain if you solve this in convected Helmholtz, right? You could solve this using convected Helmholtz, but you now see some hydrodynamic waves, in fact, also appearing. So let me now dig a little more into what really the LE can support as type of waves. Actually, the LEs can support three types of waves: acoustic, hydrodynamic, and entropy waves. So, and each of them have a different dispersion relation. The acoustic dispersion relation is the classical one, which you see here with mean flow, where this is basically the, depending on the angle between the wave and the flow. So basically the wavelength will be the longest if the wave travels exactly with the flow. It will be the shortest if it travels against the flow, and then you have a continuum between them. So this is given by this relation. And then you have also the hydrodynamic and entropy waves, which have the same dispersion relation. And it's exactly the same, except that there's no 1 plus here. And this 1 plus makes it very different. This is basically a wave that is convected with the flow. There's no upstream hydrodynamic or entropy waves. It really travels with the flow. I mean, it represents, in the end, linearized hydrodynamic perturbations that are being convected with the mean flow. That can be expressed in time or in Fourier domain. Note that the entropy and hydrodynamic waves, which are purely convected, are ruled by the same dispersion relation. Now we will have a look at two graphs which are a bit complex, but if you can understand this, basically, I think they are very revealing of the physics at play in the LEs. What you see on the left is basically a representation of the wave vectors, so k bolt, in a uniform mean flow that you see depicted here, which is oriented like that. So basically, a longer vector means shorter wavelength, right? Larger k, shorter wavelength. So this is the upstream wave, acoustic wave. This ellipse here is the dispersion relation of the acoustic waves, right? This is short k, so this is long wavelength. This is the acoustic wave traveling down with the flow, and this is traveling upstream. Sorry, excuse me. Excuse me, we're having a course here. We have to keep the doors open. Thank you. And what you see here in blue is actually the hydrodynamic waves. So you see that there's no wave that actually travels upstream. They're all being convected. They just doesn't exist. And you see that the hydrodynamic wavelengths are typically, I mean, for this Mach number here, 0.5, they're exactly of the same order of the magnitude, the same scale as the upstream wavelength. And as you move transversally to the mean flow, you see that basically the wavelength goes to 0. So this is an infinitely small wavelength, and here it's a small wavelength of the order of magnitude of acoustic upstream wavelengths, so the shortest wavelengths. That's for Mach, but that's Mach number dependent. So that's for a fixed Mach number, looking a bit at the different scales at play. But now you can also look as a function of the Mach number. So now if we take Mach 0.5, you are along this line. And what you see here is the range of admissible acoustic waves from this is lambda. So this is the largest acoustic wavelength. So this is the downstream wave. And this is the shortest acoustic wave. So this is the upstream wave. And what you see here is this continuum from, from the upstream wave here, which wavelength is equal to this one. You see that they are of the same size, so they are meeting here. And then there's the whole continuum going down to 0. So all scales down from 0 to this wavelength are the admissible hydrodynamic and entropy waves supported by the LE at Mach 0.5, and this is the range of admissible acoustic waves. So when you see this, gray area of ranges of acoustic scales and ranges of hydrodynamic scales, you realize that basically, well, what do you think? I mean, you see two regimes, right? You see a regime here and a regime there. And what about their interaction?
One can excite the other.
Yeah. So you can already think that, just thinking of scales, right? In this region, actually, they share a lot. I mean, they are similar scales. So you can imagine that they will couple, again, engineering perspective, but they will couple more easily, or they will interact more, right? In this regime, basically, you see that there's an order of magnitude at Mach 0.1. There's an order of magnitude. These wavelengths are 10 times smaller than the smaller acoustic wavelengths. So you can imagine that the two phenomena will sort of coexist, but there will be lesser interactions. So I think this is a very, I mean, I've worked on the LE for a while, and this graph helped me a lot, actually. I mean, we generated this also because we had difficulties to understand the scales at play, and it helped us a lot once we were able to think in terms of that graph. So let me now put it in practice. I'm showing here an example of what the LE can solve, and it's a non-standard acoustic problem, because you would typically think of using the LE to, model the problems of acoustic sources, monopole dipoles, or vibrating surfaces in non-uniform flows, right? But you can also use it to inject actually hydrodynamic perturbations. So you can, something I didn't say is that the acoustic perturbations are typically compressible waves, whereas the hydrodynamic and entropy perturbations are sheared waves. It's a bit like in solids, you have P waves and S waves, and here it's a bit the same principle. If you look at the dispersion relation, I mean the fundamental solutions of characteristics of hydrodynamic and P waves, they basically, their vector is oriented perpendicularly to their direction of propagation. So it's really a shear wave. Whereas for acoustics, so a plane wave will vary like this. So this is fundamentally different. So you see it here. We're injecting, in this example here at Mach 0.3 and Mach 0.5, we're injecting actually a gust that you see there. It's a gust that is propagating with a zero angle of incidence, but you see this is Vx on the left, Vy and pressure. You see that it only has a Vy component because it's a shear wave, right? It propagates along X. Oops, sorry. I'm always clicking the wrong button. It propagates along X, but it's Y-oriented. And it's hitting a thin plate. And it's the interaction of that gust, right, which has a purely shear wave with that thin plate that creates an acoustic pressure. If I remove that plate, there is no acoustic pressure here. It's zero. And I do the same exercise at Mach 0.5. And what you can see here is basically the different scales. The wavelengths at Mach 0.5 of the hydrodynamic wavelengths oriented with the flow is exactly the same as the upstream wave, yes, upstream acoustic wave. And you see here that at lower Mach number, the hydrodynamic length scales are smaller. So in this example, we are in this regime or in that regime here. And you see automatically from this example that the LEs is more than just acoustics. It contains also hydrodynamic and entropy perturbations. It's a quite rich operator, in a sense. So this is basically an example where you can use the LE for leading edge noise, which is quite original as an application. I don't know if you have any questions on this or. Yeah.
Is there any imposition of a Kuta condition at the trailing edge in here, or just you see what I mean?
Yeah. No, there's no imposition. Now I think that numerically you don't necessarily need to impose it because I mean.
Maybe, I don't know.
You're ensuring that all quantities are finite by nature, but that's a sort of.
Okay.
Yeah.
But it's always complex.
Yeah. Things. So here it's mostly leading edge.
Right.
Okay, now about the LE again. So key message to bring home: it supports both acoustic, hydrodynamic, and entropy waves. Entropy and hydrodynamic waves are sheared waves, only convected with the mean flow, which have very different length scales. It depends on the Mach number regime. Now, it's a very rich operator, but it's this sort of the fact that it's a very rich operator also leads to some issues. Typically Kelvin-Helmholtz instabilities. You see here an example that's a jet, that's an axisymmetric calculation of a jet engine. So what you see here is the bypass duct, and here is typically the hot jet. And in essence, this is the actual mean flow. that you see here, so 160 meters per second. You see here the shear layer. And this is a solution obtained at 2 kilohertz. And you see that basically you see some hydrodynamic length scales here, some acoustic length scales, but this is actually polluting the solution. I didn't show it in this slide here, but actually the solution you obtain here in the shear layer depends on the resolution. So if you change the mesh, and I also certainly aligned with the remark of Miko, that, you know, whenever you have a numerical model, you know, try to introduce some variations to see the sensitivities. That's something you can do. You know, you change your mesh size, you will realize that basically it's an instability because it keeps growing as you increase the resolution, essentially. So LE suffers from Kelvin-Helmholtz instabilities in parallel shear flows. That's mostly at low frequency. So if you increase the acoustic frequency here, you will have less issues. That's actually a limitation of that physical model, because in the LEs you assume non-linearities and viscous terms. In reality, what will happen is you will have vortex shedding, you will have some vortices created, and this phenomena will be, you know, naturally damped and will not give rise to instabilities in Navier-Stokes. But that's quite an issue with the LEs, actually. And it can affect both time and frequency domain solutions. There are significant, many papers in the literature that mention that frequency domain solutions are stable. It's actually not true. They are more stable, but they can be also impacted, actually. So different strategies were proposed. Some proposed to remove some terms of the LE, quite arbitrarily. It's called mean flow gradient suppression, not the best approach, in our humble opinion. And then there is basically a more systematic approach, which consists in basically using characteristics to keep the LE form and removing the hydrodynamic waves from the LEs. And that's what is called the acoustic perturbation equations. Now we can look at, again, we have a small MATLAB code and we coded these different operators and we look at them. And if you put all these operators, LE, AP, that's the verb variant for of the AP, and that's Goldstein, so that's the linear as potential equation. So this is in 2D for an isothermal flow, it could be 3 unknowns, if I'm not mistaken. And this would be 3 unknowns as well, and this is 1 unknown. So this is, you know, much more economical because it's a scalar operator. And here all operators are equivalent. I mean, you obtain the right solution for a uniform flow, right? Now, more interestingly, and that's also Sophie showed this graph, if you move to a sheared flow, then you start to see differences, right? The LE and the AP and Goldstein, so that's basically propagation in potential flows, start to differ from the LE. Because there's a high frequency assumption actually in the APs, which makes it, you know, not equivalent. And typically the difference is usually acceptable in mildly sheared flows and higher in strongly sheared flows. So it all depends on, you know, which accuracy you want to reach. And what I mean mildly shear flows, it actually, it's always in relation with the wavelength. So you always have to put in relation the gradient of the mean flow in the mean flow variations, the scales of it, to the wavelength. And it even gets worse when you look at hot flows. So that's the LE, which we take as a reference here. So that's a point source in a hot jet. These are the AP and Goldstein equations, and for this operator, I mean for this mean flow, they actually look very much alike. And you see that basically we don't capture well the directivity of the source in low frequency. When you move to a higher frequency, it gets much better. Here, actually, we hardly see any differences. And that's a generality. I mean, in the high frequency limit, these operators, AP and LPE, will converge to the LE solution. You know, when the wavelength becomes really small compared to the variations of the mean flow, then you will converge. but differences between, you know, these sort of approximate operators are usually emphasized in non-isothermal flows. So basically, you can use those operators in sheared flows as long as they are mildly sheared, again, to put in relation with the wavelength, and isothermal. If you use non-isothermal flows, you should really be careful if you have strong density variations.
In the above figures, your monopole is placed at -2 or 0.
Yeah, it's placed at 0. It's actually only half of it. I mean, we're not showing the. It's in the middle of the jet.
It's symmetric.
Yeah. I think here it's 2D, which it did a bit, but in theory, yes, it's at 3D. So now moving on to, I have until 5? 5, huh? Okay, thanks. So, you know, I mean, you can, when you talk about solving these operators, you could think of modeling them in frequency domain or in time domain, right? When you do acoustics, you always have this duality, and you know, depending, sometimes if you did your PhD in time domain, 10 years after, you will always like, it's a bit like, you know, it's dogmatic somehow sometimes. But if you look at things in a neutral way, frequency domain is well suited for tonal noise. I mean, if you only have just 1 or 2 frequencies to compute, right, it seems evident that it's the right approach. Linear problems, obviously, but you can use it for broadband as well, right? You just need to compute many frequency lines to obtain, you know, frequency sweep with enough details in your spectrum. Consider the way to avoid instabilities. It's true that, I mean, I can speak personally, I was very frequency domain guy, and when you move to time domain, I mean, there are numerical errors or sort of approximations that you can manage in frequency domain, you know, it works. And when you move to time domain, it's more sort of demanding, right? Because those errors, they tend to pile up as you know, as time increases. And I mean, it's again a very engineering generality that I'm giving here, but it's when you have very difficult problems to solve, sometimes it's easier to address them in frequency domain, although it's of course a very, you know, very general statement. Solutions are globally coupled, so basically you're you know, when you solve an acoustic problem, the solution here and the solution at the other part of the room are somewhat coupled, and you need to resolve a big matrix. It's usually an implicit problem. You need large memory, you have large memory requirements, right? You need to basically invert a big matrix at some point. So it does not scale well with the problem size, but on the other hand, it scales with the number of loads. So if you have one problem and you have 100 ways to excite your system, you can scale there, right? You can factorize your problem once and solve your 100 load cases. So it scales with the number of loads, and that's very interesting in many occasions, but it doesn't scale with the problem size. Time domain, on the other hand, is well suited for broadband. You can do nonlinear problems, obviously. Now, I would say, again, very general statement, it usually requires, you know, being very careful about discretization errors and stability. It's sort of forgives less, but it has good scalability with problem size, but you can solve only one load at a time. Now you also have two main classes of spatial discretization schemes, right? There's this unstructured methods and the structured methods. Again, depending on where you did, what you used during your PhD, somehow you have. It's funny to see that years after you have this sort of preference. Structured methods, it's easier to achieve high accuracy because you can reach low dispersion, low dissipation easily. It's a simpler data structure that leads to better optimization, especially on GPU. Now, designing grids for complex geometries is time-consuming and requires care to maintain grid quality. This is the major hurdle for the larger deployment of structured methods. Although I should say that recently there has been a breakthrough that people use more and more what we call immersed boundary methods, where you kind of take your structured grid and you place your CAD or your geometry into that immersed grid. So somehow it's sort of hybrid because you're structured in most of the domain and you're kind of unstructured along, you know, those immersed cells that you need to treat in an unstructured way. But you can still gain, you know, for it kind of reduces the complexity to only D-1, where D is the dimension, because your immersed cells will only be on the surface, so their number will be limited. But then there's the class of unstructured methods, which are mostly there because they are suitable for complex geometries. Now that automated mesh generation is improved, you know, it's easier to generate unstructured meshes when you have a complex. So I think this is in industry usually the most widely used method, right? Finite volumes and finite element methods. In terms of the numerical method, you have the finite difference method, the finite elements, the discontinuous Galerkin method, and boundary elements that are used in acoustics. And you know, in terms of whether they can cope with complex geometries, non-homogeneous media, whether they are high order accurate, I think the two most general techniques are the FEM and the DGM. And where FEM is mostly used for elliptic problems, so again, that's a generality, but you know, just to keep it maybe a bit caricatural, but make sure you understand at least the main figures. I would say FEM is most widely used for elliptic problems, so problems formulated in frequency domain, whereas DGM is typically used for time domain, so hyperbolic problems. But again, there are versions of DGM which are also applied to elliptic problems, but I'm summarizing. About far-field boundary conditions, that's also very important when you do you know, finite elements or DGM or even finite difference. You want to have an efficient absorbing condition. There has been several ones, so I'm talking here of the ones dedicated to acoustics, not buffer zones and so on. But for acoustics, you have the infinite elements, the absorbing boundary conditions, and the perfectly matched layers. I think PML is the most common technique nowadays. I will not enter too much into the details because we will talk about this in depth on Wednesday, where you will have to a code of a 1D PML and you will play with it and you will be able to understand you know, the principles of it. I'm just showing an example here of it's not necessarily a flow application, but I couldn't resist to show you my Tintin shark submarine. So this is basically an example of how the process can be simplified for unstructured meshes. Because in commercial software, SimCenter 3D, not to name it, you can do this mesh generation in one click, basically. It's fully automated. So basically you have a skater here. There could be flow, right? I mean, not in this application. I mean, it's not fast enough to sort of you need to include the mid flow convection effects.
Do we know the speed of Tintin?
I don't know the speed of Tintin submarine. And just from the size of the propeller, I'm just guessing. And so the surface meshing is, you know, starting from the CAD, the surface meshing is automatic, and then what we call is you know, you have to create a volume around this, right? Here I'm just computing the scattering of a sonar, for instance, like a plane wave coming from another submarine, you know, trying to detect maybe a competitor of Tintin willing to find the treasure of Rackham the Red, I don't know exactly. And you want to surround this scatter, but in you know, in an efficient way, and you can use what we call convex hulls. So you need this to be convex, right? You cannot sort of wrap it really too close, right? You need a convex shape around it, otherwise waves can enter and go out. It's not well posed, right? And you can do that automatically. mesh it, and then you use a tape measure, and this is all automatic, right? You just have to keep the mesh size pretty much. And then you need to enforce an appropriate operator here. So you could use BEM, boundary element method, which is in the end the only exact, directly to Neumann, the only exact operator on the external surface for acoustics. But it's fully coupled. So you know it will be dense, it will be a dense matrix. It's too expensive. So we use approximations. And you can use infinite elements or ABCs, absorbing boundary conditions, or you could use PML, and that's what we do here. We use PML, and the PML is generated automatically from this surface, but you will learn more about it on Wednesday. And this is the result of the scattering of that plane wave on the shark submarine. About mesh generation, so there are different types of algorithm. I think there has been a lot of progress in that area in the last 20 years. Now, in most commercial software, this is more and more automated. There are advancing fraud methods, Delaunay regulations, and some methods even use octrees and quadtrees, these immersed boundary methods that I mentioned, or even conformal approaches. Yeah, you can also have, anisotropic meshes in star CCM plus. Now they really have, anisotropic mesh refinement that follows basically. You really see the mesh following the shock waves. But this is a bit, the most advanced meshing technologies. Yeah, I will skip this. So I'll take a bit of time now to talk about frequency domain finite element methods. So that's one approach to solve acoustic problems, is to formulate them in frequency domain and use them to resolve them. So I'm going to talk mostly here of linearized potential theory. So that's the LPA operator I talked about at the beginning, which is widely used in the industry for concrete aeroacoustic propagation problem. Like the nacelle aero engine problem you will look at with Kortian over there tomorrow morning, if I'm not wrong. So Kortian will actually show you through in the software hands-on how it works from A to Z to actually model such a problem in a commercial software. So here we're solving a simplification of the linearized Euler equations. So that's describing perturbations in potential mean flow, a near-rotational mean flow. So there's only one variable, which is the velocity potential. So it's a very, it's a quite lightweight operator. And it's used in several commercial simulation codes like ours, but also ACT30M, in COMSOL they have it as well. So this is used daily across the world to really solve problems of convected acoustics. I think the LEs so far is mostly used in labs, whereas really routinely in industry people use the LPA operator to define, for instance, the liners in the nacelles. You will see that with Kortian. So it's a classical Galerkin approach. I will not insist on the formulations itself. So yeah, to mention the problem that to introduce the problem that you will solve with Kortian, you see here a nacelle. So that's an aero engine. So typically Rolls-Royce or any aero engine manufacturer would be interested in designing the acoustic liner here. You would all know that if you look carefully at the nacelle, you will see a perforate plate with a honeycomb inside, and actually the nacelle itself and this treatment is there. The nacelle is there also for acoustics, and the liner is there only for acoustics, and it's designed to absorb, for certain regimes, certain flight configurations, especially when the aircraft is close to the community, right? When it's flying really high, then it's less of a problem. So I take off and landing mostly. and cut back. Yeah, this liner is tuned to basically make sure that mostly tonal noise is reduced. And if you hear aircraft today, I mean, when they fly over Brussels, which happens a lot, you don't hear tonal noise that much. I mean, that's my experience at least. You don't hear you hear mostly airframe noise actually, yeah? and broadband noise from the fan. It's most...
And the turbine. There's still a bit of whistling that is a turbine.
Yeah.
But it's downwards.
Yeah. So anyway, so to model this here, the mean flow can be assumed to be potential. I mean, as a first order of approximation. Of course, there's a boundary layer, and that we'll mention that later. But you can assume with a good approximation that it's actually a potential flow. So you can use the linearized potential equation. You can use that operator and solve it with finite elements in frequency domain and obtain good results. So you have a fan here, and the fan is represented by duct modes that Christophe presented this morning. So you have duct modes here. So it's really purely an acoustics problem. We don't solve the fan, right? We consider that you know, we just want to compute the transfer functions for each of those duct modes pretty much, and we will use a non-reflecting condition there, and we will test different liners and maybe run an optimization on the liner properties, resistance, reactance for a given flight configuration, and from that we will try to manufacture something. So that's how it's done in practice. There's still one subtlety, which is that the interaction here of the boundary layer and the acoustic liner is very important. And basically, it's not trivial to write so we don't want to resolve the boundary layer in our operator. We're just going to consider a uniform flow. I mean, we're just going to remove it because it's too small of a length scale, right? It's going to kill our simulation if we have to model it. So we simply truncate the boundary layer, and then we basically apply what we call the Myers condition, which in the end represents the continuity conditions between what happens above the vortex sheet and the line surface. So it's a kind of, it's considering an infinitely small boundary layer, and it writes the continuity conditions so as to represent correctly the influence of the liner on the acoustic quantities. So yeah, about the shape functions themselves, I will move. I will not insist on this because we will revisit this on Wednesday during the hands-on session with Simone. But basically, in finite elements, the solution is continuous. You know, we construct a continuous solution across the full mesh, and for that we use typically linear and quadratic Lagrange shape functions. So these are the standard shape functions. If you did FEM, I think most of you did some finite elements. You will use these shape functions. But actually, for acoustics, high-order methods yield significant benefits. Why is that? It's because acoustics is mostly about how do you say, smooth solutions. So representing linear combinations of sines and cosines, right? Pretty smooth. I mean, it's not like turbulence or shock waves, or like the gradients are mild, and it's basically, you know, the solution is differentiable, so to speak. And in that context, if you want to approximate a smooth function, if you do polynomial regression, it's more efficient to approximate that smooth function by increasing the order than by using many small elements with a low order, right? You want to have a big element and use high order polynomial regression to do an approximation of a smooth function. So high order methods are in general preferable for acoustics. And in finite elements, we have what we call PFEM. So you probably heard of HP adaptivity. Does anyone of you know what HPFEM stands for? What is H, what is P? Apart from Simone? No? So no one of you have ever heard of HPFEM? No. Okay. So it's basically H stands for the mesh size and P stands for the order. So when you talk about HPFEM, it means that it's a method where you can play on the mesh size and the order at the same time to basically converge to your solution. So you know, there's the classical FEM that was developed in the 70s and 80s, right? It's an old method, huh? You know that, huh? They were even solving FEM problems with perforate plates back in the days, huh? So that's really old. But I think already in the 80s and 90s, there was a new version of it that appeared where people tried to have sort of automatically driven solutions. So basically, in classical FEM, the user has to provide the mesh and he gets a solution. And then what? And then he should look at the solution and say, I'm going to change the mesh size here and let's see what it gives. But people have tried and it's not yet quite achieved. 40 years after, people are still trying to make this automatic. Basically, to have the computer itself being able to look at the solution and infer a posteriori where to refine automatically. And if the computer is able to do that both on the mesh and on the order, because in some occasions you might want to increase the order, in some occasions you might want to refine the mesh, and that depends on the smoothness, local smoothness of the solution. If you have a source or something, a singularity, you want to refine. If you have a nice sine function, a smooth function, you want to increase the order. And that's called HP adaptivity. And that's the grail of numerations, right? Numerations want you to click on one button and have the computer, you know, taking care of everything and refine where you want to refine until you get your solution converged. And you all know, if you have used simulation methods, I'm sure you have, and it seems that there are quite some experimentalists in the crowd, but I'm sure you use simulation as a tool, so you probably struggle with that, right? Yeah, Christophe. Thank you, Christophe, for active participation.
Anytime.
But yeah, the grail is HP adaptivity, but we're not quite there yet. Now there is also P adaptivity, where you say, okay, I'm not going to touch the mesh, I'm going to keep the mesh as it is, but I'm going to increase the order until I get a correct solution. And you know, there are different ways to represent the field. What we call shape functions, right? This is the sort of, how you interpolate your solution, and I won't enter into the details, especially because we'll look at that Wednesday. Something important, when you solve a finite element problem in frequency domain, so you have to solve at each frequency independently, right? And you end up with a system that is sparse, because basically, when you assemble, so this is the look at the final system of equations at one frequency before you solve it. And each of those, to simplify, here you have 200 unknowns. Each of those line represents, to simplify, a pressure point, right, that you're solving. And there is basically, what you get is a sparse matrix by contrast to BEM, which yields dense matrices. With finite element method, you obtain sparse matrices. Basically, it's because each node is only connected to its neighbors, right? When you do the assembly of the matrix, right, each node is only connected to the neighbors, and you will end up only with a few entries per row. Right? So if you have a structured grid, right, with hexas, you can already infer a priori how many rows there will be in that matrix. How many do you think?
So how many hexas do you have?
In the center of your room. So let's say you model this room with structured hexas.
Right.
How many rows will you have? How many entries will you have per row? Sorry.
8.
Which order?
Order 1.
8. No.
8. So that means in 3D, no.
I'm not understanding the question.
So basically, this node will be at the center of 1, 2, 3, 4, 5, 6, 7, 8 elements, but it's
6
connected to 3 to the cube, so to 27 nodes.
Okay.
Yeah, it's 9 in 2D.
Okay.
But basically, there will be 27, entries, non-zero entries per row, and the rest will be 0. So it's basically, the matrix is huge, but it's mostly populated with zeros, and they are very efficient linear solver, you know, libraries that can cope with that. And yeah, typical solvers are mumps or Pardiso, and you can use the backslash of MATLAB as well, which works reasonably well. But if you have large matrices, then you have to go to something else, right? So the backslash of MATLAB doesn't perform any as well as, you know, the more specialized tools. About numerical accuracy, so that's an interesting thing, I think, is that when you solve a numerical model, especially for the non-specialists, and including for the specialists, it's a hassle all the time, because we have a sort of what I would call the sort of error race. There's a competition between the errors. And somehow there is always one that is dominant, right? There is always one that is in front, but it's hiding others. So whenever you actually do something to tackle it, you know, you will suppress that error, but the one ranking second in that error race will pop up. And you don't know if it's super low or if it's just behind. And sometimes you're sort of thinking that you're going to treat the problem, but you're treating the second error in the error race. And so since the only one that matters is the first one, you don't improve your solution. You see what I mean? And that's something that is very puzzling. And I think it's the cause of millions of hours of research time loss. So there are multiple errors. There's the geometry error. So basically when you use a finite element or a discontinuous Galerkin or even finite volume and you solve it, you're not going to solve the real CAD, right? You're going to solve an approximation of it. Take the very well-known example of the scattering, of the plane wave scattering by a sphere, right? What you're actually solving is not the plane wave scattering by a sphere. You're solving the plane wave scattering by a disco ball that you use for dancing, because it's faceted, right? So there will be lots of small numerical artifacts coming from this, and this is what we call geometrical error, and it's there in the error race, but you don't know where it is. Typically, this one will tend to go up as you increase the frequency, right? In low frequency, if you have a disco ball or the complete sphere, you don't care. But as you move in frequency, then maybe you may treat other sources of error, but it will become rank first in the error race. And then there is the flow interpolation error. That's very important as well for the applications we're talking about here. You basically get your mean flow. Think about the nacelle, and you will do that with Korchan. You take your mean flow from a steady CFD, from a RANS. The RANS mesh is typically much smaller than the acoustic mesh, right? You will take it, you will use one of those magnificent tools that we have. You will click on the button, you don't really know what happens, and then it says, well, the flow is mapped. Okay. And you launch your simulation. But actually, again, you're not solving on the flow that you think you're solving on. I mean, you're solving on the flow that is projected onto the acoustic mesh. So it's another representation, and interpolation in general is really a nightmare, right? Same for boundary conditions. If you have a velocity boundary condition coming from a structural model that you want to use to simulate the radiation of an electric engine, for instance, right? You get your structural analyst will compute the vibrations from an electromagnetic /structural simulation, and he will give you a super refined structural mesh, and you will have your coarse acoustic mesh, and you will project, and there will be aliasing, you will lose. So that's another source of error. You have then spatial discretization error. That's classical, right? Dispersion, interpolation. You may have dissipation in some schemes. The time step also introducing errors. Then you have errors generated at the buffer zone, so what we talked about around that Tintin submarine, and all of them are in a race. And you have to always ask yourself, then talking about Fox-William-Hawkins, you may have integration errors, quadrature errors. You always have to ask yourself which one is dominant, and if I treat it, who's gonna come after that, and am I good enough? And that's, yeah, takes a lifetime to get used to that. So I just want to insist on this concept, right? I will just mention them briefly. So that's an example of of a single duct mode in a circular duct, where you see that you have lots of, spurious, pressure perturbations that are induced by the fact that you're not solving actually a strictly circular duct, but again, a faceted duct. So what we typically recommend is to use, whenever possible, to increase your representation of your geometry when you can, so to use quadratic elements wherever possible, if you think about finite elements. Mean flow interpolation, that's also something we looked at with Sophie, and it's quite tricky, because, I mean, at first I was thinking that actually, if you increase the resolution, if you make the mapping as best as possible, it's going to be for the best, right? But actually, there's a point where even you introduce some sort of super small length scales of your mean flow, which are actually noise, right? I mean, there also needs to be some smoothing in the mean flow interpolation for some applications, because your original mean flow is never perfect either. So it can be really very, very, very difficult. But you see, typically here, the mapping that is done correctly will give you this, and the mapping that is not done correctly will give you that, right? And you see here that there are some very small length scales that may, for instance, trigger an instability in time domain simulation. So those small details can matter sometimes. So that's a shear layer typically. About the numerical error, I will not insist too much on this, but basically just to say that, yeah, there are different regimes. So this is about the spatial error. That's a bit technical, especially if none of you are really into finite elements. But there are basically different regimes. Yeah, that your convergence depends on whether you are in the asymptotic regime or not. I will not insist into that, basically also because we will have more sensible ways to discover this with the hands-on, I think. Let me skip this. Okay, so something we worked on quite a lot here at Siemens is again this adaptivity. But we worked on adaptivity for a fixed mesh. So in many acoustics applications, you actually have a wide frequency range from 20 Hertz to 20 kilohertz, right? So that's 3 orders of magnitude in length scales. And the model preparation is difficult. So typically, what you may want to do is to generate one mesh per frequency, right? You use the rule of thumb, you say, okay, I want 10 points per wavelength to represent my wavelength. At each frequency, 20 Hertz, 30 Hertz, 40 Hertz, 50 Hertz, and yeah, I'm going to generate a new mesh, right? A very coarse mesh for low frequencies, super fine mesh at high frequencies. But that's very cumbersome, right? And instead, we want to rely on a single mesh. I mean, the most, but what people do is to refine on a single mesh. They take the highest frequency, the super small mesh, right? And they say, okay, it's good enough for my highest frequency. I'm going to use it for the full frequency range. But that's very expensive, right? Because you kind of overkill your solution at low frequency by orders of magnitude. So what we worked on here is to basically use adaptive high order, to use a single input mesh, a coarser mesh, right? And then let the orders decide and vary across the frequency automatically without asking the user. So we worked on this using a priori error indicators, and then later on we extended it to having directional orders. But I will just show some example. It will be more. So this is a nice feature of I don't know if you know Gmesh. That's an open source mesher that is developed at Liège and Leuven. And there's a nice feature. You can give it a picture or a Jeep, you can give a picture of yourself or a bitmap or anything, a JPEG, and you can generate a mesh. Basically, it's a bit geeky, but it's funny. So the mesh density will depend on the pixel. So if it's black, it will create, various. So you can put your face or any picture you like. It's very geeky, but anyway. And so I put a Tintin model, and that was the technique pioneered by Hergé, because Hergé, la ligne nucléaire, yeah. You know, he created the contours of his characters. He introduced that technique for drawing. So you see here that basically the mesh size is super small, where the Hergé drew the contours. And so let's say this is my mesh, because in some occasions you have, you know, very small geometry details, or, you know, in most practical applications of engineering applications, you have very small mesh size and very large elements, right? Both are coexisting in a mesh. So you want to have a technique that can tackle that, handle that efficiently. And then basically we take that mesh, we call our a priori error indicator, which is basically just a rule of thumb, which is automatic. I mean, it's a bit more complex than that, but essentially we use linear elements here. So just an approximation, linear triangles, 3 degrees of freedom per triangle. And in the larger regions where you have large elements, we use here order 5 or 6. So that means we have 40 doves per triangle or something like that. So this is a much richer element than here, because we suspect it will have to, you know, represent more information pretty much, right? And this is automatic. And then we just propagate a plane wave, and we actually look at the actual error. It's 0.78%, and the target was 1%. So that's, and then you can vary the frequency, and you can put mean flow also on top of it, and it will also handle that. So here it's just for the fun. I'm introducing another Belgian example.
Example where the notion of flow takes its importance.
And here the notion of flow takes all its sense, yeah. Although it didn't resolve the the hydrodynamics part of it, yeah. Yeah. Yeah, that's just to mention that. Yeah, just to mention that when there is mean flow, you also have different length scales depending on where the direction. So if you are transverse to the mean flow, your wavelength, your length scales will be larger than if you are upstream or in the direction of the flow, aligned with the flow, right? So along the flow streamlines, the scales will be shorter. So you can do anisotropic order adaptivity, meaning you can increase the order only in the direction of the mean flow, provided your mesh can be reasonably aligned with the flow streamlines. And that's what we do here. We basically, only increase the order in the direction of the mean flow, and we keep, so I think here it's a mix of order 4 and 9 in the same element, but we enrich the solution only in one direction. You can do that as well. So this I mentioned here. So that's an example where it's quite an old engine, JT15B. It's probably I don't know, from the 60s or. But here we have a comparison. Here you see so we're modeling the nacelle on this part here, and just want to show you, you will see that with Korchan, but just to show you that we have some comparison with measurements, and you see that you obtain reasonable, you know, estimations of the noise radiated with these methods. This is why they are used routinely in industry. And this is the effect of the liner. So this is hard wall, and then you can introduce different types of liners, and depending on the angle, that's the far field radiation. You obtain different spectra, and you can tune your liner based on that. And yeah, now the main issue with finite element methods is the memory, because you still have to solve that big matrix at the end, and those linear solvers made for sparse matrices, they don't scale very well, meaning if you try to solve on a cluster, you will have lots of overheads. You typically can't, you can probably solve them on 20 cores, I mean 20 MPI processes, 30, 40, but not 4,000, right? Not like finite volume, it doesn't scale that well. So there are other approaches, and we're also looking into that, namely domain decomposition methods, in which you introduce physics, right? You kind of separate domains and you introduce some non-reflecting conditions using the physics at play. Whereas, you know, those linear solvers, like imagine the backslash being able to do NPI, it's purely algebraic. Yeah, another significant source of aircraft noise is sound generated at exhaust. Here, well, typically you want to use the LE, and because there are some, it's a non-isothermal flow, there's a strong shear layer, and you cannot use the LP for this kind of applications. And there we have tried other techniques. So that's an example of an exhaust geometry. So just to show you in practice, that's the Mach number. It's the same example that you saw before with the instability. You see here the vorticity magnitude, so that's basically the rotational of the mean flow, and you see that you have a strong rotational component in the shear layers, in the two shear layers, yeah, I won't enter into the details, but basically we were able to generate some frequency domain solutions solving the LEs in frequency domain for this type of application, but it's extremely demanding from a memory standpoint. Yeah, we're still trying to industrialize that, so to speak. So this is still sort of POC and not yet in the commercial software. And yeah, so should I stop at 5, did you say, or 5:15?
5 or 5. I think it was 5.
It was 5, right? Yeah. So briefly, I mean, just to mention also that you can also use discontinuous Galerkin methods that are now getting more and more popular in acoustics applications. I won't enter into the details, but it's also a higher order method. And the main difference with FEM is that the solution is discontinuous across the elements, as the name indicates, right? Finite element method constructs a continuous solution. So whatever, even if you get a rubbish solution, it will always be solution. It will always be continuous, sorry. With DGM, if you get a rubbish solution, you will really have completely discontinuous fields, right? Because it's only through fluxes that your solution is made continuous. It's a kind of crossover between finite element methods and finite volumes. It's kind of finite volumes with high order capacity. Just want to show some examples. So here, yeah, a DGM code was used at ISVR to represent to solve the same problem of a nacelle, and here we used our DGM code to solve the LE, or again the sound refraction from shear layer from a hot jet, and you see here a snapshot of the pressure. So this is solved in time domain. So here, the advantage of the DGM is that in time domain, if you use an explicit time stepping, it scales, meaning you can really put that solution on a cluster, and it's more computationally demanding, but you can basically, you know, if you can solve larger problems, so to speak. So that's why this kind of methods is getting traction now. Whereas, you know, in the CFD world, people use finite volumes, but in acoustics, you want to use higher order methods, right? It's really beneficial. And DGM provides you a scalable framework to do that, to achieve higher order accuracy in space and in time. while keeping scalability. So that brings me to the end of this presentation, and thank you for your attention. It was a long day, and I hope these 3 lectures could bring you, you know, more flavors of I mean, deeper insight into aeroacoustics. Thank you.
Thank you.
I don't know if there are questions.
I always have questions.
Yeah.
You mentioned this race between the errors. Now, for the lame experimentalist that I am, are there some recipes that allow to identify which one is winning the race? Like if I vary this, if the error goes this way, then it means that the dominating error is of that kind, or?
Yeah, there are ways.
You see what I mean?
Yeah.
To make sure that I'm precisely not working in the wrong direction.
I mean, if you keep everything the same and you have different frequencies, you know that yeah, you know that geometry error will not pop up in low frequency typically.
Okay.
You know also that, I mean, one way to look at things is always again looking at wavelength, and like if your geometry has 10 points per wavelength, you can consider, you know, that it's reasonably correct.
Did you see what I mean?
Yeah.
Kind of black box procedure. You have your code, and you vary this parameter. And
I mean, you vary time step, you see that you get the same result. It means that time discretization error is not first in the race.
Okay.
So buffer zone, you put your buffer zone further away,
right?
Or you increase, you know, the number of layers, or you know, the power of it, so to speak. If you see the solution doesn't change, it's basically solution invariance is your
golden gray or pretty gray.
Essentially, yeah, it's looking at sensitivity.
Right.
As soon as you move something and you see that the solution changes, then you know you're. I mean, it's like Charles Holmes.
Then I'm hitting the possible winner of the race.
Yeah.
Okay, thank you.
So follow up to Christophe, is it like when we do like experimental work, we do like subwall or global sensitivity analysis or something? Is there a specific sensitivity analysis to follow in this case, or?
So usually sensitivity analysis, you do it on a converged simulation to check other quantities, right? Sensitivity to the diameter of your duct, position of some, I mean, you see what I mean?
Well, I guess you're referring to sensitivity with respect to the numerical parameters then.
Yeah, between all these 4 parameters, we change one thing and we do something, but like, is it following a specific set of equations which we need to use for the model, or is it like global sensitivity analysis method, regression variance based method or something?
No, I mean, so that's what, so when I say sensitivity, it's a bit misleading. Because again, when you do sensitivity analysis, normally it's with a simulation that you trust. Okay, you trust your simulation, and we're not there yet. When you look at this, you cannot use the simulation for doing sensitivity analysis yet. You want to do error analysis, right? And for that, the thing is to change the mesh size, change the time step, and you know, refine your geometry. Change the interpolation method, put your buffer zone further away, or your Fox-William-Hawkins surface, move it. And if you see changes, then be careful.
No, I mean, I'm just confused because of the dot can be something which we don't know which might affect just
Yeah, I mean, this is pretty general, but depending on your
specific requirement.
Yeah. I don't know, Fox-William-Hawkins, there will be a quadrature rule used on each of the cells, number of quadrature points. You see what I mean? No.
Just to conclude this slide from again last week, I would put first bullet point as bug in your code, that you should make sure that your code is accurate itself. Second,
and then we put your phone number after that.
With your code, you are solving the right problem. because probably you may visit what we call user error. They set up a model, but they use wrong solver for come with wrong expectation.
Yeah, you're right.
Second bullet point that I put on the top.
Yeah. So basically, yeah, it's true. It's a very good point actually, because there are bugs. Yeah, unfortunately. And you're right. I mean, in a sense, if there are no bugs, then the numerical solution you get is the one that then it's a sort of modeling issue, right?
Mm-hmm.
But it's very difficult to do it right. Still. No. All right. Thanks a lot.
Thank you.